My name is Niliana Akpinar, and I'm presenting our paper, The Effect of Differential Victim Crime Reporting on Predictive Policing Systems. This is joint work with Maria de-Arteaga and Alexandra Chouldechova. Police departments have been using crime mapping for several decades. However, only more recently, computer-aided predictive policing software has come to rise. One example for this is the software sold by the company Predictive, which attempts to predict inner-city crime hotspots based on historical crime data, just using the location and time of those events. Systems like this have come under scrutiny, both due to a lack of transparency and concerns about biased outcomes. And we will be concentrating on the biased outcomes in this talk. Previous work in this area has concentrated on the potential for dangerous feedback loops that might arise when arrest data is used to train these systems. Lum and FAccT demonstrate how using data on drug arrests in Oakland, California as inputs to the predictive policing algorithm could result in high concentrations of policing in racial and ethnic minority neighborhoods. At the same time, Ensign et al. Use an EARN model to theoretically analyze how these feedback loops arise when arrest data is used. On the other side of the story, we have Predictive themselves, who proceeds to say that their algorithm is naturally unbiased and states that the data they collect and use in the system is primarily victim data rather than arrest data, and also excludes drug-related offenses and traffic citation data in order to remove officer bias. So overall, there seems to be a disconnect between the criticism so far and the data Predictive says they use for their system. And this has inspired the current study, where we basically see what happens if we would take the whole system and train it only on victim crime reporting data. And we demonstrate that in that case, the differential victim crime reporting rates throughout the city can lead to geographical outcome disparities in hotspot prediction, with no arrest data used whatsoever. These results are based on a simulation study. We conduct our simulation patterned after district-level victimization and crime reporting data from Bogota, Colombia. This data is used to simulate reported and unreported crime events. The reported crime events are then used to fit a model similar to the one used by Predictive and predict crime hotspots. Since we simulate the whole data set of events, we also have access to the unreported crime data. So together we have a sense of the ground truth crime distribution that we can use to compare the performance across districts. As I already said, our analysis is based on a crime simulation patterned after Bogota, Colombia. And this district-level victimization and victim crime reporting data is collected by Bogota's Chamber of Commerce. Approximately 10,000 participants were part of this, and the participants came from all socioeconomic statuses and all 19 districts of Bogota. The reason why we chose Bogota for the study is mostly the availability of the data, because crime statistics that include both information on victimization and crime reporting, such as the National Crime Victimization Survey in the US, are often not published with high enough spatial resolution to get a sense of differences within a single city. So now let's talk about the model we're using for hotspot prediction. We rely on a self-exciting spatial-temporal point process model, which is very similar to the model employed by Predictive. This kind of model is characterized by its conditional intensity lambda, which has two parts. The first part is the background intensity, which is the spatial distribution of independently occurring crime events. And often for this, what is used is a Gaussian distribution that is very flat, so with very high variance. For each point that occurs from this background intensity, there is some likelihood that an aftershock crime happens in the immediate vicinity. So For this aftershock intensity, we define the triggering function, and the triggering function places a smaller Gaussian distribution around the event that already occurred, and an exponential distribution of the time from the original event to the offspring event. And this type of model is commonly used for modeling inner city crime, but it originated from earthquakes, which is why we say aftershock in this case. After this model is fitted, and the whole city is split up into individual cells of, in our case, 1 kilometer times 1 kilometer, we can get the expected number of crimes within a cell at time t+1 just by integrating over the area of that cell. In order to minimize the error introduced by model misspecification, we use the same model or very similar model to simulate our synthetic crime data as follows. We start with a superset of data points by just taking a very high intensity self-exciting point process and sampling events from that point process. And then in the second step, we subsample those events based on each district's victimization rate and the scale population of that district. This has the benefit that the resulting set from step 2, which is the set of reported and unreported crime data, is still distributed according to a thinned out self-exciting point process. And this is the part that allows us to have an idea of a ground truth distribution of crime and a ground truth of crime hotspots that occur throughout the evaluation time steps. In the third step, we subsample the events from the second step based on each district's victim crime reporting rate in order to get a set that only contains reported crime data. Then our hotspot prediction procedure works as follows. We train our model based on 4 years of reported crime data. And since our model is entirely a parametric model and the likelihood is intractable, we do this with an expectation maximization procedure. In the second step, we then predict the crime intensities in each of the grid cells that we put on top of the Bogota map. And we select the top 50 cells as hotspots, which translates to about 5.7% of the city area. Then we proceed and add the data for that prediction day to our model without updating the parameters of the model, of course, and repeat steps 2 and 3 for a total of 189 evaluation days. So let's look at some results. Here I picked out 2 of the Bogota districts that are Kennedy and Usaquén. And what I'm showing here is the relative number of predicted hotspots. That is the number of predicted hotspots in a district divided by the number of true hotspots in that district. Each point here represents a distinct evaluation day in a given simulation run. And we conducted 50 runs of the simulation, which includes the data generation that we start with initially. There are a whole lot of different models in this plot, but what is interesting for now are the models S1 and S2. S1 is the self-exciting point process that we trained on all of the data, so both the reported and unreported crime data. And S2 is the self-exciting point process that we trained on only the reported crime data. And the first thing that we observe here is that S1 performs decently well, which basically means that both the mean and median here are very close to 1, and 1 is obviously the number we want to achieve here, because that is exactly, 1 means that exactly the right number of hotspots have been picked out in the given district. However, if we move to S2, which only operates on the reported crime data, we see some disparity here. We see that in Kennedy, the relative number of predicted hotspots seems rather high in S2, And in fact, 126.1% of the number of true hotspots are predicted on average, while in USA-CAN, we see a particularly low number. And in fact, only 20.4% of the number of true hotspots are predicted on average here. Basically, that means that our model that is only trained on reported crime data tends to overpredict the number of hotspots in Kennedy, while it underpredicts the crime hotspots in USA-CAN. And if we look at the other districts as well, the direction of this disparity seems to align very well with the victim crime reporting rates. While Kennedy has a particularly high victim crime reporting rate of 28%, particularly high in comparison to other districts, USA-CAN has a low victim crime reporting rate of only 13%. So overall, what this suggests is that when we train on only reported crime data, the model learns to overpredict the number of hotspots in high reporting areas, while it underpredicts the number of hotspots in low reporting areas. Okay, let's talk about another equity measure. Here, I picked out the same two districts that are Kennedy and USA-CAN, but on the y-axis, I now have the minimum true crime rate in predicted hotspots. That is the true crime threshold to be required, that is required in order for a cell to be predicted as hotspot. Each data point here still represents a distinct evaluation day in a given simulation run. And again, S1 is the model trained on all crime data, and S2 is the model trained on only the reported crime data. For S1, we see that the threshold in both districts is around 0.5, which means that on average, a minimum of 0.5 crimes are expected 0.5 crimes are enough for a cell to be predicted as crime hotspot. And mind that this number is very low here because we scaled the population to speed up the runtime of our simulation. If we move over to S2, we see the same pattern we saw before. For Kennedy, the number is particularly low, and a minimum of 0.27 expected crimes are required to be predicted as a hotspot. In USA-CAN, on the other hand, a minimum of 0.62 crimes, expected crimes, are required to predict a hotspot. And this is a striking difference, because what it implies is that in order for a cell in USA-CAN to be predicted as a hotspot, it requires more than double the expected crime. And this difference, again, aligns really well with the victim crime reporting rates if you look at it as at large. So how can we fix this problem? The first idea that comes to mind is rescaling of the predicted crime rates according to the victim crime reporting rates we know from the survey. So that would mean we take the reported crime data, we train our model, we make intensity predictions, and then we scale those intensity predictions by how much crime we know is missing, and only then select the top 50 cells as hotspots. And this is exactly what we tried, and what is denoted as model S3 in these plots. And we see here that in many cases, the rescaled model S3 is closer to the full data model S1 than the original model only trained on reported crime data S2. However, if we look at the bottom right plot in USA-CAN, we see that the rescaling here seems to overcorrect. And this is an interesting phenomenon that can be led back to the fact that the rescaling increases predictions in a district by a fixed amount. So for each cell in this district, the predicted intensity is scaled by the cell amount, irrespective of how much crime was actually unreported in that particular cell. So then in some way, that means that the noise that we have here is scaled as well, which can lead to a scenario where roughly the right number of cells is picked out, but the wrong cells within the district are picked out. So overall, that means that the rescaling approach does not really solve the problem here. It does seem to make the problem a little bit better, but it doesn't seem to solve the problem. And in order to recover the actual cell-wise true crime distribution, we would need a much finer survey that actually has a cell-by-cell rate of victim crime reporting. However, a survey like this in practice would be unattainable because it would require a cell-by-cell rate of victim crime reporting. And even that said, even a survey like this, where we know the crime reporting rates on a district level, is not available in most cities. So this whole rescaling idea really doesn't help all that much. So the last thing we explore in this presentation is what happens if we replace the self-exciting point process model with the within cell moving average model on crime counts. And I picked out the same districts and equity measures again here. M1 denotes the model that is trained on all crime counts. M2, the moving average model that is trained on only the reported crimes. And M3, the model that is only trained on reported crimes, but then rescaled by the surveyed crime reporting rates. And what we see is very interesting. We see that S1 appears to perform very similarly to M1, S3 very similarly to M3, and S2 very similarly to M2. Across all the districts, basically. And this is interesting for two reasons. First of all, it implies that this moving average model, although it is way simpler than the self-exciting point process, and although the data we're training on is generated from a self-exciting point process, this model seems to perform fairly well. Maybe the added complication of the point process isn't really necessary here. And the second point is that the simple moving average model suffers from the same equity problems as the self-exciting point process did before. So now, finally, we draw some conclusions. In the study, we find that differences in victim crime reporting rates can lead to geographical bias in common hotspot prediction algorithms, even when no data from arrests or police-initiated contact is used. This can lead to misallocation of police patrols in the form of over-policing as well as under-policing. Particularly, it can lead to cases where some districts in the city have higher police presence than, although other areas in the city have effectively higher crime rates. We tried to solve this problem by rescaling, but this was not particularly successful. Unsurprisingly, not particularly successful. And ultimately, we don't really have these surveys for a lot of the cities these systems are deployed in anyway. So it's really an open problem how we could solve this. And then finally, the results of the study here should be seen in a socio-technical context, of course. We know that victim crime reporting rates are driven by socioeconomic factors, types of crime, and other demographics. However, much more work is needed for an in-depth discussion of how the results we saw in the study interplay with all of these factors in the Bogota-specific context. And we will have some more details on this in the paper. However, we see the main contribution of this work as a first demonstration of the disparities that can arise when training on victim crime reporting data. That's it. Thank you for listening to this talk, and I'm free to answer any questions.